Perfect. Well, that's good. So we're finally on. I don't know why this was happening, but when I clicked on that link, I was the only one in the room. But I left and came back, and here we all are. So that's great. So we can start class now. I'm going to attempt to share my screen. Let's see if that works. All right. Go to share screen. Push a bunch of buttons. And then let's see if I can get my slides up here. All right, can everyone see the slides? And actually, I can't see, but anyway, can everyone see the slides? That's my question. All right, I hear a bunch of messages, but I can't see the messages. So yes, okay, good. So we'll go back to the slides here. All right, so welcome to our abbreviated meeting on protein separation. Oh, just a sec here. I'm gonna make sure that I am recording my voice here because there we go. Just in case the actual screen recording fails. In theory, Blackboard should be recording this for us, but I've been having a lot of computer trouble this morning. First time doing this in a while, so I guess, as always, I should have written detailed notes last year when I was doing this, but I will remind myself of all the wrinkles. So today we're talking about protein separation. And for example, often you want to catch a particular type of fish. And a lot of fishermen will say, this lure will catch rainbow trout and it won't catch the other fish in the lake and those kind of things. You try to be specific for what you are hauling out of a mixture. You might have a net with a particular size, so you get the big fish, not the small fish, that kind of thing. And it's almost the same with proteins. We think about their properties. If you were separating proteins, and this sort of presentation will focus on the idea of enzymes, but there are many different kinds of proteins that you may wish to isolate. Receptors, regulatory proteins for DNA, all of these kinds of things. We're going to talk about enzymes because they're the easiest, and they're the easiest because one easy way to find them is just check for the reaction they catalyze. Because the first thing you need when you're looking for a protein is a way to find it. We need an assay. So what is an assay? An assay is just a measurement. It is just a way to measure for a particular protein. And so we have a whole bunch of, oops, using the wrong pointer there, a whole bunch of assays here for different proteins. For example, invertase, one of the very first enzymes that was investigated kinetically, they just followed, Michaelis Menten just followed the change in optical rotation, which was easy to do back before the turn of the century. However, now that we have UV-vis spectrometers, we can actually follow reactions by UV-vis absorption. So some reactions, the change in the molecule will give you a change in UV-vis absorption, and that would be great. Phosphodiesterases, you can use radioactive phosphate, and you can follow the formation of free phosphate through liquid scintillation methods, or basically radiation counting. There's all kinds of ways you can do it. For example, if you're purifying for hemoglobin, just look for the red color. So there's lots of ways that you can use to find a particular protein. But really the best way to find a protein, if it's an enzyme, is to just look for the reaction. You could have a tube with sucrose in it, you know it's optical rotation, and as you purify your enzyme, you take every single fraction of the various purification efforts and you put a drop of each one into different tubes, and you see if in any of them this reaction happens. And if this reaction happens, that means an enzyme with the activity of your goal enzyme is in there, and it's likely the enzyme you're looking for. So here's a number of assays for a particular, if you're looking for chymotrypsin, right? You could just use this marker compound right here. This is just paranitrophenyl acetate. It's an ester bond, and most proteases will hydrolyze esters because esters are far easier to hydrolyze than an amide, and it's very similar chemistry. So most proteases will cut an ester at some rate. So as long as you see accelerated ester hydrolysis, it means that there's an enzyme there that does that, and that might be your protease. Unfortunately, there's many enzymes will cut this. Carbonic anhydrase will cut esters like this. Really, it could be any protein, not very specific, but it might be the assay you're using. This particular structure right here is designed to be more specific. But it reacts with both trypsin and chymotrypsin, but not other proteases. So if you're trying to look for trypsin or chymotrypsin, this would also detect trypsin. This one here, though, is more specific for chymotrypsin. So if this ester is being hydrolyzed and the UV absorption would change as that went from an ester to a carboxylic acid to change a little bit, enough to pick up in a UV vis spectrometer, then that would tell you that there's chymotrypsin. This is the native protein itself. You could be looking at that, but that reaction, not as easy to follow, giant molecules involved. This little assay molecule would be the way to go. So you need some scoring system. So this is a scoring system. And if you see the absorbance going up in your sample, you might say, my enzyme is there. So you just need a way to find the enzyme. And looking for a reaction it catalyzes is often the best way. There are many assays. I won't spend too much time on this slide, but there's direct assays, coupled assays, continuous assays. A direct assay is it catalyzing the reaction? So for example, lactate dehydrogenase is a famous assay. The UV absorption of NADH, you can see the structure there going from an aromatic system to a not aromatic system has a big change in the UV vis. And basically, if you're looking at around 340 nanometers, you would see 0 to 60 as I went from NAD to NADH. So if I had a tube that was full of lactic acid and NADH, or sorry, full of probably pyruvate and NAD as, wait a minute, I've got this backwards. This is NADH over here. Please correct that. This is NADHC, NAD, there's the extra H. So if I had it full of lactic acid and NAD, nothing's going to happen until I have my enzyme, and then you would see a rapid change. If my enzyme was present, you would see this rapid increase in the signal. Now, you might have a very complicated system where you can't look at 340. There could be other things that are absorbing it. And often in that case, you can use a coupled assay where the NADH, after it's produced, undergoes a further reaction. Here I've used a fluorescent group that can react by itself with reducing agents. And there's no reducing agent in the sample until we make NADH. Then NADH can transfer electrons to this fluorescent group and release this fluorescent molecule, this coumarin. And so this is the fluorescent signal here. So a coupled assay is where we have coupled the product of the reaction with a further reaction that we can then look for. So it's no different than the direct assay. It's just that there's a subsequent step. So sort of like developing film. The direct signal is the light hitting the film, and then the next step is you developing the film. Back when we had film. A continuous assay is where you're just following chemistry as it goes, and there's other ways you could do that. You could do a stop assay where we add the enzyme, wait 1 minute, then stop it. You could stop it just by adding strong acid, change the pH enough that the reaction stops, and then you have all the time in the world to analyze it, right? So if it's convenient to just look at things in the tube, fine. If you want to, say, use a 96 well plate, you're probably using a stop assay where you put everything in the wells, you wait 1 minute, you stop the reaction, and then you analyze all 96 wells of the plate. So it really depends on what you're doing. So just remember, direct assay, you're just looking for the exact reaction the enzyme catalyzes. Coupled assay, you're doing subsequent steps after that to other chemistry, tells you that the product is there. You could do it in a continuous fashion where you're watching the signal form over time. You could do it in a stop fashion where you stop the signal. So here's a stop assay. You stop it, and maybe you analyze it with a slow technique like HPLC, high performance liquid chromatography. Look, 8 minutes to do each run. So if you want to take it at 1 minute time points, you're going to have to stop it at each minute and then analyze each of those samples leisurely over the rest of the day. So it very much depends on the practical nature of your system. What are you doing? So I just want you to know those words so you know what people are doing when they talk about their chemistry. They're going to be talking about whether it's direct or indirect, and they're going to be talking about whether it's continuous or stopped assay, and that's just really letting you know the general method. But once we have it, we have a way to detect your enzyme. So you've got your enzyme sample. You put it through some kind of a purification, and all purification is separation. I'm going to take the sample that's in here, I'm going to spread it out over 40 other tubes. Somewhere in those 40 tubes, hopefully, is my protein. And you can see here, here's your 96 well plate. I have the assay solution. I take a little drop out of each one of these tubes and I put it in the assay solution. The assay solution might have the chemistry that the enzyme catalyzes for. There might be further chemistry there that detects that. But whatever's happening, this imagine, say, a paranitrophenol reactant, and you can see the yellow color of the nitrophenol form. Doesn't matter what you are doing, a signal forms, and there I see it. I know that my enzyme is in these tubes, so maybe it's right here in the experiment. I would recommend, rather than eyeballing it, you actually use a plate reader or UV vis spectrometer. That's all a plate reader is, and you quickly see exactly where the reaction is happening. So I would then take these tubes, collect them, and know that they have been enriched in my protein of choice. I'm just going to go back to my screen here and make sure there isn't a whole bunch of questions, or because I can't see it. How do I get this up here? So there's people, there's chat. Oh, there we are, everyone. Okay, no one's saying they can't see my screen or anything. That's good. That's, I'll always feel free to, actually, I can't see anything that comes up that you type when I've got my screen full of the slides. So I recommend that you call out with your voice if you have a question, or if it all goes to pieces for you here. And now, there we go, it's back on the screen. Good, I hope it's back on the screen. So that's really what we're doing. If we can detect the protein, then I can try all kinds of different ways to separate it, and at least I'll know where it is. So how would you separate it? You've got to find something that's different about your protein from the proteins around it. I could perhaps separate you. I could take this whole class and I could say, I'm going to separate them by their affinity for stinky cheese. Some of you out there like stinky cheese, I'm sure. So I would set up a buffet, and the buffet would just be full of stinky cheese. And I just let you walk by. And you know what? Most of you probably walk by that real fast, but some of you will come out of the room a little later with a plate full of stinky cheese. And so time-wise, the people who paused at the buffet because they enjoyed the stinky cheese will come out later. Well, we can do the same thing with proteins. We can put them through a material, a column of material, and some proteins will have a greater affinity for interacting with that material. And so they're in the solvent, they're interacting with the material, they're in the solvent. How long do they spend in each situation? That will change how fast they move through the column. If they have a greater affinity for the column material compared to other proteins, they will come out slower. And so the proteins will all come out of that column kind of in order. There's other ways we can separate proteins. Solubility. So we might be able to change their solubility. We could hit their isoelectric point. Maybe they'll come out, precipitate when they're neutral. Maybe we change the salt concentration around them. High salt concentration, like all those sodiums, would neutralize negative charges on the surface of the protein. Chlorides would neutralize positive charges on the surface of the protein. If you had high enough salt concentration that they were all sort of forced into the protein there and reduce its solubility, it might come out. So we could do something called salting out, where you just add a ton of salt and a lot of the proteins will precipitate a solution. You can separate based on charge, so change the pH, change the charge. We can separate based on affinity, so we could have a very specific affinity for a material and separate according to that. We could separate according to size. There's all kinds of ways to separate. Look at these 10 proteins of glycolysis here. They all look different. Maybe we can separate them differently. Okay, now I am going to, let's go to the next page if it will do this for me. There we go. So One way to separate is salting out. So that would be this technique here. And that's where we use high concentrations of salt. It's often the first cut you will do. If you've got a protein-rich mixture, you put it in a high salt concentration, and there'll be this precipitate. You centrifuge it down, you now have a large amount of the proteins have been isolated. You could check the soluble proteins that remain. You could just take that solution and throw it at your assay and see if you get a signal. Hopefully you don't, or a very weak one, and you've shown that you have removed the protein and it's down in that mass. Then what you can do is dissolve that solid mass in a much more dilute solution. So you don't use salt water anymore. You use, say, fresh water, a dilute buffer solution, and you dissolve up the proteins. And now you've got the proteins dissolved again, but they still are polluted with a lot of salt. How do you get the salt out? You can use dialysis. These are dialysis chambers. They have a dialysis membrane on the surface of them. And what that is it's just a sheet of material that is semi-permeable. All right, it will allow water and small molecules to pass through it freely, but will not allow large molecules like proteins to pass through it. So if I had this solution that was rich in proteins and salt from the salted out proteins that I had redissolved, I could just put it in a bucket of fresh water, of pure water, and everything would exchange. The salt would fill the entire volume of the bucket. All the small ions would fill the entire volume of the bucket, but the proteins would remain in this small location. And if I then just threw that out and put it in another bucket of pure water, any little salt that's remained would dilute out, but the proteins remain exactly where they are. So I can purify large biomolecules from small molecules with dialysis. So I could do that. That might be the next step. So I just salt out. So that separates my proteins from all the sugars and all the other soluble things. I then use dialysis to get my proteins separated from the salt I used to salt them out. And now perhaps I'm ready to go. And one of the classic ways to purify things in chemistry is with a column. These are various prepared columns with different materials on them. And you would pump your protein into this column for a short burst and load the top of the column with your protein. And then you would start pumping a solution of something through. It could be just a buffer solution, or it could be a buffer solution in which you're gradually changing the pH. It could be that you're gradually increasing a salt concentration. It could be that you're gradually adding a molecule that will compete with the column for the protein and release it. There's all kinds of techniques to use, but I'm putting a changing condition through the column, or maybe not changing, maybe just a steady flow, but the proteins move at different speeds. So here's an example. You've got your column loaded with material. You start flowing through, we call it the effluent, and you can see things start to separate, and eventually, protein C is coming out first. After a while, protein B would come out. After a while, protein A would come out. And you've separated them if you're lucky and they come out that neatly and separate from each other. So columns are really common, and here's some common columns. We can use a ion exchange column. So this is about ion exchange. And what is ion exchange? Well, I could have one ion stick to a column and then exchange it for another, knocking it off. But really what we're talking about is charge. I have a protein and it's got these groups on it. All right, so when you look at this group right here, you can see that this protein is 1, 2, 3. It's got 2 against 1. It's positively charged at pH 5. All right, so the protein is positively charged at pH 5. So I put it through a column that has, positive charges on it. Have I done this right? So it's positive pH 5. It's just going to go right by. But the negatively charged protein is sticking. So maybe we should start at pH 9. So at pH 9, this protein is negatively charged and it is sticking. Oh yeah, see, I see the pH is going down here. That's good. So at pH 9, I have my protein is negatively charged. Other proteins that are different might have different charges. So my protein sticks because the column has positively charged groups on it that aren't pH sensitive. They are always positively charged. So negatively charged proteins stick to my column and all the other proteins wash away. And then I change the pH and my protein might be neutral, but it still doesn't come off. But then I finally change the pH all the way to 9 and my protein comes off. So what I'm doing is I'm selecting by charge. As I go through those charges, when my protein changes charge and no longer sticks to the column at that pH, that's when it comes off. You can see that I've imagined going from 9 to 7 to 5, but in reality, you would set it up so the pH changes gradually. And there would be that point, that exact point on the protein where the pH is exactly where it needs to be for your protein to come off. And other proteins would come off at different pHs, and hopefully everything would separate well that way. So if your protein has a charge, you could change the pH, and as long as you were in a range where it didn't destroy the protein, you might be able to separate with an ion exchange column. One of the benefits of the ion exchange column is that they're inexpensive. So it's often one of the very first purification techniques you'll use, because you could use a really big ion exchange column with a lot of protein and get that first cut where you've got a whole bunch of proteins that are the same charge as your protein, or the same isoelectric point basically, or close to it. You'll get down from 10,000 proteins to 1,000 proteins. So your first load is going to need a bigger column. Why not use the cheapest material? So maybe we'll separate by charge first. Then we might separate by size. So this is a size exclusion column. So we have a material that is macroporous. It's got many pores, all these pores in it. And what happens is, depending on the size of the pores, so if you look at this, what I've done is I've imagined that there's big pores and small pores. If you are a small molecule, you can fit in the big pores and the small pores. So what you see is a volume equal to almost the entire space, because you can fit everywhere. If you are a big molecule, you can't fit into any pores. The only volume that's available to you is the volume between the beads. You see a much smaller volume. The example I like to use is, imagine that we put all of you in those, those samurai suits that you have, for in September when you have a little festival outside and someone's got a little booth, and you put on a samurai suit and you run at someone, you bounce off each other and you fall down. Let's imagine we put you in those giant suits, or put giant balloons around you. And some of you had them and some of you didn't. And I sent you down a long corridor with many doors, and the doors were all open into other rooms. Some of you could only be in the hallway because you can't get through the doors. So if I had you randomly moving around, you would just bounce off the walls, you would bounce off the doors, you would eventually get to the end of that hallway pretty quick, because it's the only space you can experience. The people without the giant balloon suits could go into the classrooms and bounce around there for a while before getting back out to the hall and continuing on. So since they're experiencing a greater volume, they will move more slowly. So if I put, if there's 1 mil of volume for this protein might be encountering 10 mils of volume. So if I put 1 mil through the column, this protein's out. It takes 10 mils through the column for this protein to come out. Maybe it takes 7 mils for this protein, maybe it takes 3 mils for this protein. Different volumes depending on the volume that protein can experience, which is based on size. What size exclusion gives you is big comes out first, because it's been excluded. And small comes out last, because it was included everywhere. All right, this protein, went down the street, it was invited to every party. It took all night to get to the other end of the street. This protein was only invited to half the parties. It took them less time to get to the end of the street. This protein, never invited, got to the end of the street really quick. And so that's kind of the nature of it. So big proteins will move faster through a size exclusion column. And so you can then separate by size. So there's a high molecular weight, and there's your low molecular weight. So time, we're waiting for time, Then this protein came out earliest, time passes, this protein came out, time passes, this protein came out. You can usually track protein coming out with just simple UV spectrometry, because proteins have lots of groups that absorb UV light. So when they come out, the UV absorbance should go up. So that's size exclusion. So I could separate by charge, and get a cut of proteins where I found the activity of my enzyme in a much smaller amount of protein, still not pure. Then I could separate by size. Now I know they're all about the same charge, at a given pH, because they all came out with my target protein, but now I'm separating by size. So now maybe I only have a handful of proteins remaining that are the same isoelectric point and roughly the same size. Maybe, this peak here is 20 proteins instead of thousands. And then I could use something called an affinity column. And an affinity column is where I have a specific group, something that might be similar to the substrate of your protein, for example, or something that your protein binds strongly to. And I have a column that I have chemically attached that group to the column. So maybe here is the group that something maybe looks a bit like ATP, if you have an ATP binding protein or something like that. Your protein goes through, all the proteins that don't stick to the group that you have on the column just wash through. And then there's your protein. And then I can change the conditions. I could put through a competing group, like a competitive inhibitor that would compete for the site that's using to bind the protein. I could change the pH. I could use a higher salt concentration. There are a number of ways that you could weaken this interaction. So you wash through all your proteins, only your protein sticks. Then you change the conditions to weaken that interaction, and only the protein that is there comes off. So you put through your proteins, everything washes through. Wash, 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 wash. Nothing more is coming out. Then you change conditions at this line here. Often people will say, put through the release buffer. What's the release buffer? It's the buffer that has something in it that knocks off anything that's stuck to the groups on the column. And there's the one protein that you want. And affinity columns are expensive. You would like to only use a small one. So you would like it to be perhaps that you've already mostly purified your protein before you go for it. So that's the idea of using this lure here. That's the magic one. What's it called? Greg's Demon. Greg's Demon. That's the one to catch the big trout. You want to be specific for the big trout in your fishing competition. Use Greg's Demon on the end of your fishing line. So you purify by charge. Maybe we purified by size. Now we purify by affinity column. Now, there's lots of ways to improve this. There's all kinds of technology. One of the major money makers in biochemistry is selling other biochemists ways to purify proteins. So if you're ever reading a catalog or at a conference, you walk down the hall and there'll be lots of people with all of their great ways to purify your protein that they're trying to sell you. And people who develop better ways to purify proteins, maybe you can do it in a single step with this technique here, only costs money, right? You'll make money doing that. So here's an idea of a typical workflow. I have my sample, I put it in the top of the column, and maybe it ended up in these 4 tubes here. These 4 tubes here showed a strong signal in my assay, which means the protein I'm looking for is here. So I just take those 4 tubes now, a lot less protein now, and I put it through so this was ion exchange, maybe I'm putting it through size exclusion now, and my activity only showed up in these 2 tubes. So I took those 2 tubes, I concentrate them down, I load that in this column here, maybe this is my affinity column, and after I put through my release buffer, maybe the signal only showed up in these 3 tubes, and then maybe that's the pure protein, maybe. And so obviously purifying proteins is a lot of work. At every stage, you might be denaturing it, oxidizing it, destroying it, digesting it. You have to be careful. Many times I have been involved with this. I have had to work in what's called a cold room because they want to keep everything at 4 degrees to maximize the life of the protein. So you're doing all of your chemistry at 4 degrees. And that doesn't mean that the column's refrigerated. No, the whole room is refrigerated. You literally have to wear a parka while you're doing your chemistry. And let me tell you, sitting on a seat for 12 hours in a room, there's no parka that's parka enough. You will get cold. But hey, sacrifice is necessary for science. But in the end, you get your protein. And that's the goal. So an important definition in all of this is the word activity. You've heard me say that already. We're looking for the protein activity. If someone says protein activity, the activity of a protein is what it does. But it can also be used for how much of it there is, all right? What is the activity of the basketball player? An activity, what a basketball player does is he or she puts balls in hoops, all right? You know basketball players are around if balls are going through hoops. All right, so that's the activity. Balls are just sitting around on the floor of the gym. Add a basketball player, balls are going through hoops. So add a football player, no balls going through hoops. For some reason, they're running with the balls and crashing into each other. They're not going through hoops. So the activity is what the protein does, but activity could also be the amount. So if someone says the activity is 10 hoops per minute, they mean there's enough basketball players there to give me 10 balls through hoops every minute. If it's 20 hoops per minute, you might presume there's twice as many basketball players. So activity is another word for the amount of an enzyme. And this, of course, comes from a day when, and even now, you might not know how much protein is in there. All right, for example, I have 1 milligram of brown powder, and I know it has 134,000 international units of activity of that enzyme. And from the exact same manufacturer, you could have another gram of brown powder, and it has 128,000 international units of activity, because they measure their brown powder before they sell it. And you'll see that quite often. The gram of enzyme that you get will have how many international units of activity are in the bottle or in a gram. And that tells you how much enzyme is in that brown powder, because nothing's ever perfectly pure. If it was perfectly pure, it would cost too much. So this is a mixture that's highly enriched in your enzyme, guaranteed not to include things you don't want are in there. But obviously, this one's a little more pure because there's more activity per gram than this one. So activity could be amount. If I add a certain amount of this enzyme to a sample, I will get 134,000 hoops per minute. And the definition of an international unit of activity is 1 micromole of product being produced in the reaction per minute. So the international unit of activity is 1 micromole per minute for most enzymes. Some enzymes catalyze reactions that aren't easily characterized in micromole per minute and things like that. And so they would actually have a different definition of a unit of activity. You would consult the International Union of Biochemistry and Molecular Biology. They'll tell you what the unit of activity for a particular enzyme is. But for almost all soluble enzymes that do chemistry that we are familiar with, the international unit of activity would be 1 micromole of product appearing per minute. That is activity. There's also specific activity. So, for example, I dump in some enzyme and I see a certain activity. But if I knew how much enzyme I dumped in, like exactly how many milligrams of enzyme, then you could know how much activity there was. So, for example, I've got 10 basketball players, right? And they're dumping 20 baskets per minute. That's 2 baskets per minute per basketball player, right? That's the specific activity. If I double the number of basketball players, so I got 20 basketball players, and I double the amount of hoops per minute, the specific activity didn't change. It was still the same per basketball player, but I had doubled the amount of basketball players. So activity is the rate of reaction. Specific activity is the rate of reaction per amount of enzyme, measured in milligrams, measured in moles, whatever you want to measure it in. So it's not unlike density, okay? This is a kilogram of water, right? Or you could say water weighs 1 gram per milliliter, right? So a gram per milliliter, that's a property of water. Specific activity is a property of the enzyme. If you have perfectly pure enzyme, you will have reached a maximum specific activity. So there is a specific activity for a given enzyme, a pure enzyme. Activity would always increase if you added more enzyme. Specific activity shouldn't increase unless you're making the sample more pure. So let's talk about this idea. I'm starting off with a big mess of protein. I took 1 ton of worms, I ground them up, I ended up with 4 grams of protein, and in there somewhere is the protein that I want to do research on. I check the activity of my sample and I see that there is 100,000 units of activity in this sample. But when you divide that by 4 grams, what you have is 25 international units of activity per milligram. So that's the specific activity for this sample. It has 100,000 units of activity, but not a very high specific activity because it's got a lot of protein. I put it through my purification system. Maybe this was ion exchange. I changed the pH from 6 to 9. At some point in there, my protein came out. So here's the protein signal, lots of protein that's not mine, lots of protein, no, lots of protein that's not mine, but my assay picked up a strong signal here. I would point out, I also got a little weak signal out here. There could be other proteins that light up your assay. And that is a possibility. But this is our protein here. I think we're looking for the big signal. So I will take these tubes. I might only take these big ones. Yeah, take these middle three. Throw out the little edge ones because they're not really going to help much. So I take the core of my protein signal and I put it through size exclusion. Now I have a sample. Well, before I did that, I went from 4 grams of protein to 300 milligrams of protein, 0.3 grams of protein. The total activity is 75,000. So I lost 25% of my protein, because I didn't take that little one, I didn't take that little one, and maybe you're also counting some of this non-specific stuff here. But my specific activity, though, per milligram is much greater, 10 times more pure, you could say. I purified again, and by size exclusion, all the other proteins, this is the ones that keep. And look, I end up with 100 milligrams of sample at the end, 65,000 units of activity. So I'm from 100,000 to 65,000. I'm losing stuff along the way, but I am 3 times pure, 650 units per milligram. Well, then I take this sample and I put it through the affinity column. And you can see what happens here. We have all the proteins that aren't mine, and then the protein that's mine. And there is the sample. I finally ended up with 8 milligrams, but this is pure. Let's imagine it is pure. 8 milligrams, 55,000 units of activity. So I started with 100,000 units, 4 grams. I ended up with 55,000 units. So I got 50% of my protein out of this in 8 milligrams. And presumably, if all of those 8 milligrams were my protein, I have 6,880 units per milligram. And you might know this. You might have this written down, that if I have a specific activity of 6,880, it means my protein is pure. I've hit the maximum. So that's what specific activity is. It is the activity per amount, which is really, if you have 100% of your enzyme, that would be a specific characteristic enzyme for the activity for that enzyme. So why is all this important? Well, if you're mining for gold, look at that wonderful environment. Let's dig a hole. There's billions of dollars in gold in there. But guess what? It's kind of worthless to you until you take out the little bit of it that's rich in gold. So that's kind of a bit like salting out. I'm gonna dig out this whole mountain. I'm gonna turn it into a giant hole. I'm gonna end up making giant piles of rock that isn't gold. And out of that, I'm only gonna take the rock that is rich in gold. And that is worth money. I send that off to a factory, which use various purification techniques to make pure gold. And that is worth a lot of money. So it's not unlike this chicken. That chicken is full of protein, but very little of it is lactate dehydrogenase. I can grind up that chicken and extract the proteins. So I've left behind all the fats, all the sugars, all the bones. I have a very rich sample of protein here. That's worth some money, but not as much money as further purifying it to give this standardized, purified lactate dehydrogenase that you could sell to someone for their research or diagnostic purposes in hospitals and things. So how much is that chicken worth per pound? How much is this worth per pound? This is worth a lot more per pound. How much is dirt worth per ounce? How much is gold ore worth per ounce? How much is gold worth per ounce? You can see what purification can do for you. If you were purifying, you might want something to do the work for you. This is a basically, I guess the word we would call it a combi flash. It's just a machine that will run your column for you. It's a low pressure liquid chromatograph. It's just going to pump liquid through this column. It's best, so look at that. It's all modular. You can add modules here, but here's the diagram that best explains it. You've got this. You take this sample here and you inject it into this loop, and you'll fill this loop with sample, and it'll go out to waste. Meanwhile, the solution is flowing through this valve and it's going this way to your column. So now that, eraser going here. Now what you have is that loop is filled with sample. And then I change the valve. I switch the valve. What the valve's going to do now is it's going to pump the water through the valve to the loop, through the loop. The loop's going to go to your column now. So that little pulse of protein that was stored in that loop will end up on the top of your column, go through your column. As things come out the bottom, they'll go this way over to, UV monitor. You see the protein coming. Conductivity monitor would tell you about salt concentrations if you're running a gradient that way. And as things come off the column, they end up in a fraction collector. And so you can inject a known amount of sample. You can change the solvent. You got all these mixtures, different pHs, different ionic strengths. You're changing the fractions of them. That's how you'll get those ramps of solution. You run it through the column. You basically set up this machine, press go, and it will give you 50 tubes. And hopefully your protein has, it's in some of those tubes all laid out for you, ready to go. So that is a nice machine. Isn't that better than standing in front of a column with a bunch of test tubes collecting drips off the bottom, which my graduate school, you're just sitting there collecting drips off the bottom. If you have a machine like this in your lab, it'll do your stuff for yourself while you can write grant applications. And you can spend a lot more money. This is the exact same system with way more stuff attached. And I invite you to go through the diagram, but you can see that it can have multiple columns. So you can have all the columns sitting there ready to go. You can have many, many solutions from which you can draw samples. So which column, which solution? That would be a method that's just in the computer, ready to go. And you can go to many destinations, many different sample collectors, onto other things. So this system would be much more versatile and, just fire and forget, come back, maybe your protein is pure. So it all depends on your money, and more importantly, what's your time worth? So if you ever do become a researcher, remember, time is the true currency. So spend money on things that will let you do your work faster. So that's basically what I wanted to get across today, is that you could take a really crude mixture. You could cut out the proteins, maybe with salting out. You can then purify through a series of columns to get finally and somewhere in that, all the protein, all the tubes that came off the bottom of the column, hopefully you will find your protein. So these three here showed activity. This one didn't. So you can see in the picture, the green one did not show activity. These pink ones had increasing activity. And so you were able to find which tubes had your protein in them. So depending on what your assay is, you can find your protein and then purify it further. And eventually you've got it pure so that you can use it for your research. And we'll be seeing lots of examples later in this course where I'll be showing you where they've, say, isolated ATPase. We're actually able to get it into a membrane and use an electron microscope to watch it physically move as it made ATP, watch it spin around. They couldn't do that unless they could purify the protein, right? And to do work like that, you've got to be able to purify proteins. So that's the message for today. That's the basics of how to purify proteins. Next class, we'll be talking about ways to analyze proteins, mostly electrophoresis and methods like that. And then on Friday, we're going to talk about X-ray crystallography, a way to determine the exact structure of a protein and every single atom in space. And when you see all those diagrams, all those pictures of proteins in your book, that structure was determined using X-ray crystallography. So this week is all chapter 5. You'll notice in the quizzes, the reading quizzes, there's like only 4 questions because I took the questions for chapter 5 and I just spread them out all over the week. There's only 1 question on Friday. And that's why the quizzes are short. So that's the message for today. Are there any questions? And I'm just going to, so I can read my screen here in case someone asks a question. All right, I can't hear anybody if anyone's saying anything, so I don't know if anyone's saying anything. I'll presume there's no questions unless someone types something into the chat here. You have a question regarding tutorial. What is it? I can't hear anything if you're saying something. I'm just going to check the sound. Would you go over the tutorial assignment? I presume you mean for tutorial number 2. Let me. All right, so go down to. So I have on the Moodle site there is, there's a buffer recipe example. All that up. So hopefully you can see that on the screen now. So what I want for tutorial number 2 is a buffer recipe. Oh, that's not the one that I had on the website. Where is my, there we go, acetate buffer procedure. That'd be the one that's on the website, I think. There we go. So here's what you would have seen on the website. I just need you to make something like this, where you take your buffer, your pH would be the last digit of your student number divided by 10 plus 6.5. So if the last digit of your student number was 7, you're shooting for pH 7.2. The pKa of phosphoric acid, you'll see there's 3 protons with 3 pKa's. You'll pick the one that's obviously close to 7, the middle one. So 7.2, the pKa is 7.2. So I need 50% of one salt, 50% of the other. They need to total up to the amount. Here I want it to total up to 250 millimolar. So you use the Henderson-Hasselbalch equation to get the ratio. You solve for the amount of each protein, and then you just turn that from moles into, so I decided to use 2 liters here, but whatever you want. And then that's how many grams. I'm using glacial acetic acid, which was a liquid, so I can put it into milliliters, and this sodium acetate, that's a solid. So that's really all I had to do. So your acid would be the form of phosphoric acid that is a pKa of 7.2. So remember that you have, here, I'll just going to bring up my screen here. Just going to see if I can bring up, see if this works here. So you have, here we go, H3PO4. But there's also sodium, H2PO4, sodium, HPO4, and trisodium phosphate. You can buy that in the drug or in the hardware store. So those 3 protons came off, right? 1 proton, a second proton, and a third proton. There's 3 pKa's, 2-ish, 7.2, and 12-ish. So it's clear that these are the 2 that are at either end of your buffer. So those are the 2 salts. The H2PO4 has the pKa of 7.2, giving you HPO4. So those are the 2 salts. Once you know how many moles of one, you just use the moles per gram to give you the weight. And when you know the moles of the other, you use the moles per gram to give you the weight. So that's how you would get started on that one. So you're not using the phosphoric acid, you're using sodium H2PO4 and sodium 2-HPO4. Did that answer your question? Oh, I hope it did. Yeah, so that's, there's many ingredients to choose from there. You choose the one that's good for 7, which would be the H2PO4 going to HPO4. Once we get the moles, we take it to gram moles, convert to grams. Yes, so because remember, you're making a standard procedure. So really, it would just say to make 2.5 liters of this buffer, take this many grams of the sodium phosphate, this many grams of the other sodium phosphate, mix them in water. I invite you to include some, what you think would be good practical details, like stir it till they're dissolved, that kind of thing. Filter it, always useful. Then finally dilute it to 2.5 milliliters in a volumetric flask. And you could even add things like store it in plastic, store it in glass, whatever you think. Store it in amber glass. Some people will swear by that so that light can't change things. So there's, think of it as a standard procedure you're writing yourself, as if you were working in that lab, just for fun. But the key thing is the math. So how many, I'll be looking for, is it right around how many grams of each of the acids, or sorry, of the salts for the volume we chose. But I'm also, there's some points for making it look as I requested, which is like an instruction manual. And I want you to include a couple of typeset math equations using your equation editor, because there'll be more assignments later on, and so we might as well get that working with this small one, so that we know it works and it's not an issue when you're doing something that's more complicated, but you want to make sure that this works for you now. All right, any other questions? Grams per mole wouldn't convert into liters because grams per mole is a weight and liters is a volume. But what you'll have is moles per liter for a material, right? And you can use the grams per mole of a particular material to get the grams that are in a certain moles per liter. I can call up my little whiteboard again here. Let's see here. There it goes. All right. So, you know, if let's say sugar has, I forget what the mass of sugar is, but C12 is at 72. Let's call it like 120 grams per mole. I don't know. Let's just say it's that. So I've got some material, a sugar, not saying it's glucose, a sugar that's 120 grams per mole. I'll find one that makes it right. And I want a 3 molar solution. Oh, that's a little high concentration. A 0.3 molar solution of that sugar, and I want 5 liters of it, right? So how many grams do I need? So you could say, well, I know that I have 0.3 moles per liter times 5 liters. That'll leave you moles times 120 grams per mole. That just leaves you the grams. So if you do that math, you'll get how many grams I have to add to 5 liters to have that concentration. So just really follow the units. You'll see how they need to cancel. And if you end up with, once you follow the canceling, if you end up with grams, just grams, you know you're right. If you end up with grams mole squared per liter, something is definitely wrong. So the units will help you make sure your math is correct. Did that answer your question? All right, I hope it did. So in our case, yes, they need total up to 0.15 molar. So if the ratio is 0.5, you would need 0.075 molar of one and 0.075 molar of the other. So they total up to the right number. So you would, once you have your ratio and you know what the total is, you use those two equations to get what the actual amounts are. It'd just be two equations, two unknowns. Yeah, I'll show you real quick here. Yeah, so if you know the ratio equals, I don't know, 0.3, and you know the total, then you will be able to determine the exact amount of X and the exact amount of Y that make that true using two equations, two unknowns. There we go. Are there any other questions? All right, hopefully this all worked. We only had 30 people here, so tell everyone else that I'll try and have this recording up later today, and then they can participate, because we don't want to fall behind with that big Canada Games break, and who knows what else might happen this semester. We want to make sure that we never miss a class. So, and I'm glad we finally got the system working. I wonder if the other half of you were in fact in the room I was in, where I was alone at the start. I don't know what's going on with that, but I did eventually find a room where there were people. Hopefully it was everyone that wanted to be here. So we'll see you on Wednesday, hopefully.